let's compare these two compounds, HCl and HF. Okay, so both of them as pure substances are simple molecular materials. They're both gases at room temperature, but they both dissolve in water. And then we find an interesting difference, that this one is a strong acid, which means that as soon as it gets into water, more or less every molecule of HCl breaks up to form H plus and Cl minus. And that's what being a strong acid means, that it's completely ionized in aqueous solution. Whereas HF, it turns out, because the HF bond is a stronger covalent bond, and ionization involves breaking that bond, it turns out to be just harder for it to do. And so although it's still acidic, this is a weak acid. And what that means is that the ionization is a reversible process. So we get this reversibly breaking up to give you H plus and F minus. So the consequence of that is that in 1 mole per dm cubed HCl, the H plus concentration is 1 mole per dm cubed, because each mole of H plus breaks up and gives you a mole of H plus ions, so the H plus concentration is the same as the overall concentration of the acid. And that means that the pH is minus log of the H plus concentration will be 0. But in the case of HF, if you make 1 mole per dm cubed HF, you find that H plus is actually much less than 1 mole per dm cubed, because only a fraction of the HF molecules actually break up to release H plus. If you do the experiment, you find that the pH, instead of being 0, which we would get if this was a strong acid, because it's the same concentration of acid, 1 mole per dm cubed, but instead of pH 0, you find that the pH is about 1.55. Okay, so it's significantly higher. If we turn that back into the H plus concentration, remember H plus is 10 to the minus pH, which is 10 to the minus 1.55, and that works out as 0.028 moles per dm cubed. Okay, so you can see that only something in the region of 3% of the molecules seem to have broken up and released H plus ions based on that pH measurement. So it makes a very big difference. You can't just treat a weak acid as being kind of like a strong acid, because you know, the proportion of acid that's broken up into ions can be really quite small, and that means that the numbers that you get in terms of pHs and so on will be totally different. So we need to find a way of analysing this equilibrium and the equilibrium for other weak acids like it in such a way that we can calculate what the pH will be at a given concentration and so on. And this stuff is important because we used HF as an example of a weak acid, but there are lots of weak acids out there, particularly carboxylic acids, which you've met in organic chemistry, and also of course phenols, which you've also met in organic chemistry, both of which are weak acids. So they're very common substances, and they're incredibly important in biological processes. So we can pursue this using our HF example and just think, well, this is just an equilibrium in solution, so the obvious thing to do is to define an equilibrium constant, Kc, in the normal way, So these things are on the right, so they go on the top. So H plus times F minus goes on the top, divided by HF goes on the bottom. And that kind of equilibrium constant is so important because weak acids matter so much that it gets a special name. It is just a Kc. There is nothing weird about the way it's calculated or anything. It's just a normal equilibrium constant Kc. But when it's specifically for the ionization of an acid, so you've got to have the acid on the left and the ions that it breaks up into on the right. When it's an equilibrium constant relating to that specific kind of equilibrium, it gets called Ka, which in words is called the acid dissociation constant. Okay, so it's a very important kind of equilibrium constant, which is why it gets its own name. So you need to recognise what they're talking about if they mention acid dissociation constant. But it has all the normal properties of an equilibrium constant, because it is one. So in general it will vary with the temperature, because that's what equilibrium constants do, which means that the extent of ionization of the acid is in general going to be temperature dependent, but it doesn't depend on anything else. So that's why it's such a useful number, as we'll see. And again, as you know from having thought about these things before, the further the equilibrium is over to the right, the bigger the top line will be, and therefore the bigger the value of Ka will be. So you can use Ka values to compare the strengths of different acids, because the bigger the value of Ka, as I say, the bigger the top line, and the bigger the top line means the further the equilibrium is over to the right. So you can use Ka qualitatively in that kind of way. So what we want to be able to do is to use it quantitatively to figure out what the pH will be at a given concentration. So your first thought might be, well, let's just rearrange that expression to make H plus the subject, which we can do. So just a little bit of algebra means that we can slide the HF up onto the top line on that side and the F minus over onto the bottom line on that side, and get that H plus is equal to Ka times HF divided by F minus. So that seems simple enough, but the problem is there are too many things we don't know there. Okay, because this is what we're trying to find, but in order to calculate it, we'd have to know these three separate numbers, and that's the difficulty. So what you need to know is how you take this expression and make some approximations which let you actually calculate what the pH will be at a given concentration. So this is the exact expression, but it's not useful when you just have an acid on its own in solution. But as we'll see, some simple approximations turn it into a expression that we can actually work with. Now, the first approximation we're going to make is that we're going to assume that the concentration of H plus is the same as the concentration of F minus. So if we write down our simplifying approximations, so the first one is to say that let's let H plus equal F minus. And you might think, well, that's not really an approximation, because it's very similar to what we talked about when we talked about ionization of water. When HF ionizes, every time you make one of those, you make one of those. So surely the concentration of those will be equal. But of course what that ignores is the fact that there will be some H plus ions that come from ionization of the water. So in general, you would expect the H plus concentration to be a little bit higher than the F minus concentration, because H plus is supplemented by the ionization of water. Now actually, because water is so bad at ionizing, as we've already discussed, that difference is usually pretty negligible. The only time it will become significant is at very low concentrations, when the concentrations of these coming from the acid are so low that they become kind of comparable to what you get from ionization of water. So this is a very good assumption. Except at very low concentrations. And for A-level purposes, that's not usually something we worry about, because we tend not to have to do calculations where you have very low concentrations like that. So we're going to stick with that assumption without worrying too much about it. Now once you've made that, you can actually solve for H plus accurately without making any further assumptions, but in order to do it you have to solve a quadratic equation, and they don't expect you to be able to do that in A-level chemistry. So that's something you might want to explore if you enjoy a little bit of maths, but it's not something that you need to do at A-level. So what we do instead to avoid the quadratic equation is we make our second simplifying assumption, which is to assume that the concentration of HF is equal to the total concentration, ignoring ionization. That's slightly confusing, so let me just explain what I mean by that. If you have 1 mole per dm cubed HF, what we've said is that a bit of it breaks up into H plus and F minus, maybe only 3% or so, but a bit, and that means that the actual concentration of HF, of undissociated stuff, is less than what we'd quote as the overall concentration of the acid. But what we're going to say is, so long as that is a small percentage, then we're not making a horrendous approximation. You know, if this was 0.97 mole per dm cubed instead of 1, it's not going to make a huge difference to our numbers. And most of the weak acids that we'll deal with are actually less ionized than that, so it gets an even better approximation. So that's the assumption we're going to make, and we just need to be aware that this is only reasonable if only a small proportion of the acid is ionized. And you can't really put a number on that because it depends how accurate you're wanting to be, but obviously, you know, if 30% of your acid was ionized, so that you were assuming this was 1 molar when it was really only 0.7, that's making big errors. So we're talking about, you know, certainly less than 10%, and hopefully a lot less than that, you know, ideally less than sort of 1 or 2%. So this is only reasonable if only a small proportion of the acid is ionized. So you need to be aware of these two simplifying approximations, particularly this one. As I say, this one tends not to be something that they worry about at A-level, but this one, you need to be able to explain that it would be a problem if a significant proportion of the acid was ionized. Now, why does that help? Well, it helps, of course, because it's easy to know what the total concentration of acid is, because you can decide that. You can just decide, you know, how much acid you weigh into your solution or whatever. So this is a number you can easily know, just depending on how you made up the experiment. Putting those approximations into effect, we say that that's approximately equal to H plus squared over HF, where the change in the top line came from that first approximation that we're assuming that these two concentrations are the same, and if you multiply together two numbers that are the same as each other, it's the same as just squaring one of them. So that's equal to H plus squared on the top line. So we've got rid of one of the variables that we didn't know the value of. And the bottom line looks the same, but remember, it isn't really, because this is now the total concentration ignoring ionization rather than the actual concentration of undissociated HF. And that's our expression for Ka. Okay, so that you need to remember, because that's the useful form. But when you're asked about Ka, you need to be able to explain what the actual expression is. So don't learn this because this is only approximate. That's the definition of Ka. this is the approximation that you can use to make calculations possible. So, we said that the H plus concentration, well, we got the, okay. So we had before our experimental result that the pH of 1 mole per dm cubed HF is 1.55. So we can work backwards from that to figure out what Ka is. Therefore, so if we turn that into the H plus concentration, we already did this, I think, is 10 to the minus 1.55, which is 0.028 moles per dm cubed. And so we can then just use that and plug it into this expression to figure out Ka. So Ka is equal to, or approximately equal to, and I think it's worth just writing that just to keep reminding yourself that this is not the definition of Ka, that's the definition. But this is the approximate form that we're going to use, is going to be equal to approximately H plus squared over this, which we're going to treat as being 1 mole per dm cubed, even though we know a little bit of it's ionized, because we've reckoned that it's going to be a small enough error that it won't hugely matter, which is 0.028 squared over 1.0, which comes to 7.94 times 10 to the minus 4. And the units of Ka, moles per dm cubed squared on the top divided by moles per dm cubed, so it's just moles per dm cubed, is the value of Ka for hydrofluoric acid. So let's suppose now then that we want to work out the pH of a hydrofluoric acid solution at a different concentration. So let's say the question is, what's the pH of 0.04 mole per dm cubed HF? Okay, so we're going to use this same approach, we're going to use this approximate expression, but we've got to rearrange it to make H plus the subject. So we've got Ka is approximately equal to H plus squared over HF. And so rearranging that, we get that Ka times HF is approximately equal to H plus squared. And if we therefore take the square root of both sides, we get that the square root of Ka times HF is approximately equal to H plus. So provided we know what the overall concentration of the acid is, remember we're ignoring the fact that some of it's ionized, assuming that's a small correction, which we can ignore, and if we know the value of Ka as well, then we can calculate what the H plus concentration will be, and hence what the pH will be. Okay, so if we put the numbers into that, we get that that's equal to the square root of Ka we worked out over here, 7.94 times 10 to the minus 4, times the concentration, which we're saying is 0.04. Okay, and if you work out that number, you get 0.00564 moles per dm cubed for the H plus concentration. So you can see it's a lot less than the overall concentration of the acid, because only a small proportion of it is ionized, and therefore the pH will be significantly higher. So the pH is minus log of that number, which works out as 2.25. If it had been a strong acid, at that concentration it would have been about 1.4. So again, a significantly higher pH because only a fraction of it is ionized. So this approach is very useful for figuring out the concentration of a weak acid in solution. But the one thing you have to be incredibly careful of is remember that it hinges on this assumption that these two concentrations are equal. And that's only going to be valid provided you haven't added any extra H plus or added anything that will take H plus away, or indeed add, same for the F minus. If you've added anything else to the solution which is going to mess with either of these concentrations, then of course the assumption that they're equal will no longer be valid anymore, and this expression will therefore be completely nonsense. So this is a generally true statement. This is an approximation which is useful, but only in that very limited case where it's just the weak acid on its own in the solution. And it's very important to be aware of that, because you will come to examples of situations later where the weak acid isn't on its own in solution, and then you need a completely different approach to the problem. But for this kind of problem, that's the expression you need to know. You need to know the rearranged version of it, which is this, but so long as you're reasonably comfortable with rearranging expressions, you just need to learn this and rearrange it for yourself on demand. And you need to be aware of those approximations that fed into it. Now, coming back to this definition of Ka, you can see if we rearrange it ever so slightly, we can get this, that Ka divided by H plus is equal to F minus over Hf. So all I've done is slid the H plus over to that side. Now that's a very interesting expression, because this term on the right hand side is a way of measuring what proportion of the acid is ionized, and you can see that it gives that as a function of the H plus concentration, because you can see that as you increase the H plus concentration in solution, so if you had HF and you, for example, added some extra acid like hydrochloric acid to increase the H plus concentration, it'll drive this equilibrium to the left, and so the proportion of F minus relative to HF will decrease. Whereas if you added alkali to take H plus away, so this concentration dropped, this will shift to the right to oppose the decrease in H plus concentration, so the proportion of F minus relative to HF will increase. So this expression lets you quantify that and say, right, the ratio of the ionized to the unionized depends on this expression. So you can see that if the H plus concentration is equal to Ka, then the HF concentration must equal the F minus concentration. Right, because if H plus equals Ka, then this term on the right equals 1, because you're dividing one number by a number that's the same, and therefore the expression on the right must be the same. In other words, these two concentrations must be the same. In other words, it's 50% ionized when the H plus concentration is equal to Ka. And that sort of relationship is the reason that biologists are very keen on Ka values. So for instance, if you have got some kind of, drug molecule which, say, has a carboxylic acid group as part of its structure, if you're trying to figure out how well that drug is likely to bond to its target receptor, it matters whether that's in the unionized form like that or in the ionized form like that, because you can imagine, having a charge on there makes a big difference potentially to the intermolecular forces that will allow binding to a receptor. So you need to know whether the drug will be in the ionized or the unionized form in the particular place where it's got to bind. So if you know what the pH is in the particular cellular compartment where the drug's got to do its thing, if you know what the plus concentration is, and you know what the Ka is of the drug, which is something you can measure, then you can figure out whether it will be mainly in the ionized or the unionized form just by doing this kind of analysis. And you can see what this expression is telling you is that if the H plus concentration is bigger than Ka, it will be mainly in the unionized form, because a high H plus concentration will drive that equilibrium to the left. If the H plus concentration is lower, is below Ka, it will be mainly in the ionized form, because this equilibrium will have then shifted over to the right. So Ka is an incredibly useful number for giving you a feeling of whether a given group will be charged or not. And as I say, that plays a really important role in biochemistry. So we had for this equilibrium a Ka expression here, and we worked out that that was the value for Ka. With different weak acids, you find that Ka can vary over a huge range from something in the order of sort of 10 to the minus 3 to maybe 10 to the minus 11 for substances that you might be interested in biological systems, and bigger ranges beyond that in other situations. So like H plus concentration, it spans a huge range of order of magnitude, and that can make it kind of awkward to get your head around the numbers. So just like we converted H plus concentration into pH by taking minus the log of it in order to go from a huge range to a limited range, we can do the same thing with Ka and turn it into pKa. And you do it for exactly the same reason, that it then gives you numbers which have a relatively narrow range, so they're just easier to get your head around, but also because this is then directly usable in conjunction with the familiar pH scale. So the definition of pKa is that it's just exactly analogous to the pH definition. It's minus log to the base 10 of the Ka. Okay, so pKa is a constant in the same way that Ka is, unless you change the temperature, whereas pH obviously is a variable. And you can see the way it's going to work, that the bigger the value of Ka, as we said, the bigger the value of Ka, the bigger the top line, the stronger the acid is. But you can see, because of this negative sign, that a bigger value of Ka gives you a smaller pKa. So you've got to make sure you get used to that. So for example, if Ka was about 10 to the minus 5, then pKa would be equal to 5. And if Ka was about 10 to the minus 7, so it's 100 times smaller, so a much weaker acid, then pKa would be about 7. Okay, so bigger value of pKa corresponds to a smaller value of Ka, and therefore a weaker acid. So qualitatively it's kind of important to be aware of that. Mainly you just need to know the definition and be able to use it in calculations.